Welcome back. Let's resume our discussion. We talked about quartiles, and now we were about to start the 5-number summary. Okay, here it is. The 5-number summary consists of these 5 numbers: the lowest entry, the first quartile, median, third quartile, and the highest. So these 5 numbers, L, the lowest, Q1, the first quartile, M for median, Q3 for third quartile, and H for highest, describe the entire data set pretty well, as a matter of fact, especially when your data set is kind of symmetric and unimodally distributed, as you see in this picture. The first picture. If you have this kind of spread, then 5-number summary works out a lot, really well. Even if we have a bit of skew, like third picture or fourth picture, it still does relatively good job. If you have spread kind of the second picture, or fifth picture, or seventh picture, things can be a little bit bad, break down, but most of the time those kind of situations do not appear. Now let's discuss how well these kind of things work. Okay, one good way to compare is the range and inner quartile range, and mid-range and mid-quartile. Range is from lowest all the way up to the highest. I usually consider range as an interval from L to H, but some people prefer to have a certain number, H minus L, and that real number is called a range. I don't like it, but anyway, I don't really like range anyway. Mid-range is the average value between the lowest and the highest, L plus H over 2. But these two, range and mid-range, are not very good because they are heavily influenced by outliers. Let me show you something. Let's go over to some easy example right here that we discussed early on. And median is not affected by outlier, but mean is. For example, let's change this last entry into 400.127. Median stays the same, but mean is affected by those because you have to consider every single number there. But mean is so important in a lot of regards that we cannot simply throw away because it doesn't really work well with outliers. Also, if you really have really humongous number of data, then having 1 or 2 outliers will not affect the mean very much, so it's okay. But the range, it is really heavily affected. I mean, we used to have smallest to largest is 3.275 to 4.127, and now by some mistake who put 2 extra zeros, you get 3.275 all the way 400 to 0.127. The range is heavily affected. And also, how about the mid-range? This is the mid-range, and 201.107, and let's go back to the original 4.127, 3.701 versus 400. That we have a significant difference. So mid-range does not work very well. Range does not work very well. But if you look at inner quartile range and mid-quartile, they work okay. Because no matter what we do with this last number and create an outlier, inner quartile range is from here to there. Q1 is 3.492, Q3 is 4.032, and the outlier is outside of that. So inner quartile range stays the same as this interval, and mid quartile 3.492 plus 4.032 and divided by 2 is the mid quartile, but that'll have to stay the same no matter what this last number is. the same kind of behavior will be preserved more or less even if we have many more numbers. In other words, this inner quartile range, mid quartile, those are working okay, and they're all coming from this 5-number summary. Especially in the 5-number summary, 3 middle numbers are important, and 2 last numbers, 2 end numbers, well, they give you the range, and then they include some outliers, and in some cases outliers may mean something, so they do some work. One good way to visualize the 5-number summary is this box whisker chart. And here we go. This is what a box whisker chart looks like. We begin with a couple of horizontal line segments with the highest and the lowest values, and then we draw a line segment, vertical line segment from one to the other, and in the middle we draw a box, and box begins from Q1 and ends at Q3, and we draw another line inside the box, and that corresponds to the median. In this mathematical program, the median part is drawn with white line, but not necessarily. It could be another black line. It's okay as long as we do have those whiskers coming from L and H, and the box coming from Q1, Q3, and additional line segment inside the box which comes from M. Q1, M, Q3 corresponds to 69.75, 77, and 81.75. That's those 3 numbers correspond to these box here. Well, okay, in this box whiskers plot, if I get close to it, Mathematica automatically produces the 5-number summary. Minimum 33, first quartile 69 point something, median 77 point something, third quartile 82 point something, maximum 94. This kind of thing is called box whisker plot, box whisker chart, whatever you may call, and that's intimately connected to 5-number summary. Now, if I give you a data set and ask you to produce 5-number summary and box whisker chart, can you do that? You should be able to. It shouldn't take that long. All you have to do is sort out the data, and then knock off, you get the median, and do the same thing to low half and upper half, and you get Q1 and Q3. So you get 5-number summary. Once you have those 5-number summary based upon those numbers, you can pick up a paper and ruler and pencil, of course, and you can draw a box whisker chart. To draw the box whisker chart with Excel is rather complicated. I'm not going to assign that kind of problem. Okay, the next topic in line is variance and standard deviation. What is a variance? This first formula is the variance. X1 minus x bar is the average, mean squares, x2 minus x bar squared, all the way up to xn minus x bar squared, and take the average of all those, divide by n minus 1. And why n minus 1 is difficult to explain. It has something to do with something called degree of freedom. And this is one-dimensional data, single variable data, so divide by n minus 1. If it is double variable, n minus 2, or it's trivariate or higher, then you get n minus 3 or n minus 4, things like those. That's getting a bit too advanced, so just regard it as a part of the formula. The denominator is n minus 1. Now in the numerator, if you do not take all the squares, then some may be positive, some may be negative, so they're going to cancel each other out, and you're going to get 0 only. So that's not really interesting. If you take squared, then you can force everything into positive, then you get this variance, which is of course positive. But there's a bit of a problem because we all took the squared, we get two-dimensional quantity here. For example, if everything had been measured by centimeters, then variance will give square centimeters. If everything had been measured by grams, then we have grams squared. So in order to get those back to centimeter or grams, you have to take the square root again. That's standard deviation. it's difficult to calculate, especially if you just use handheld calculator. It's gonna take forever to calculate standard deviation of relatively large data set. It's really a pain in the rear end. So if I give a standard deviation problem, I have to make sure I do not give you too many numbers. Something like 5 or 6 numbers you can handle, but probably that's about it. And in this case, well, I'm using Mathematica, so you can use Mathematica command to calculate variance and standard deviation like that. And in a separate video, we're going to talk about how to use MS Excel to calculate variance, standard deviation, and things like that. Interquartile range too, by the way. One more comment. I don't know if anybody remembers something called mean absolute deviation. Mean absolute deviation, or just absolute deviation. And this is calculated kind of like this. Exactly the same as variance, except that the numerator is absolute value, not squared. One way to make everything into positive is to take squared, yes, but there's another way to make everything positive by taking absolute value. And this mean absolute value, absolute deviation, has its own advantage too. It's easy to understand. X1 minus x bar, the mean, and taking the absolute value means the distance between x1 and x bar. Absolute value of x2 minus x bar, again the distance between x2 and the mean. Basically we are finding out the average distance between each entry and the mean. That's what we get by taking the absolute values, or what we call the mean absolute deviation. And it's easy to understand and much easier to calculate than standard deviation. Makes a lot of sense. The problem is, at this moment it looks easy. And for example, my son is 7th grader and he does absolute deviation in his homework problem. I saw that. And well, even 7th graders can understand mean absolute deviation. However, there's a problem with this mean absolute deviation. It depends heavily upon absolute values, and absolute value functions fail miserably whenever you use calculus. And calculus is extremely powerful tool that we are relying upon in statistics. This is elementary statistics, so you don't see the effect of calculus a lot, but believe me, nearly all the formulas that you're going to be learning in inferential statistics part will be derived from calculus. And mean absolute deviation with all those absolute value functions do not work at all. Standard deviation, even though it is a little bit more complicated now, works beautifully. Square functions are okay, that's completely okay with any kind of calculus. Square root function is okay whenever the inside is strictly positive. And it is strictly positive, so everything is okay as far as calculus is concerned. Consequently, everything goes well. Now we only have one more to go in this notebook. That's the example. This is based upon really famous experiment by Henry Cavendish, 1798. Actually, I got this from our textbook. And we're going to use this example to go through everything we went through so far. Mean, standard deviation, 5-number summary, and so on and so forth. Even histogram and things like that. And we're going to use MS Excel to do some of those computation. But that's rather significant and really long, so I'm going to do that in a separate piece of video. Thank you very much. Here we go.